I made a dual low-frequency oscillator PCB with today's sponsor PCBWay. This board uses an AT-tiny to generate two separate waveforms using MCP4725 digital to analog converter chips. That way, whatever waveform we want, software can independently generate two outputs, which are intended to be slowly rising and falling voltage waveforms, usually used to control some other circuit, such as a voltage-controlled oscillator or filter, or to modulate, for example, change volume up and down for a tremolo effect, or change pitch for a vibrato effect in audio circuits. Here's the schematic of the board, starting with the power supply. I set this up to take 9 volts in because ultimately I want to use this with some guitar circuits. So 9 volts is going to be used to power op amps. Then for the digital part, I'm just using a 5 volt regulator. The main chip is an AT-tiny 1604, so that has enough program memory to generate reasonable waveforms for a low-frequency oscillator, where really what we're trying to do is just vary the output voltage up and down slowly. So in the sketch, I have a couple of data tables representing, in this case, a sine wave and a triangle wave. Then over I²C, I'm controlling two separate DACs, MCP4725. So each one has a different address, and from the data table for the waveforms, I can send out the current data point representing a certain voltage to whichever chip it's time to control. These DACs are running at 5 volts, so I'm sending that 0 to 5 volt signal out on header pins, as well as I'm using an op amp with a little gain on it to also send out a scaled up version ranging from around 0 to 7 volts. The op amps I'm using are TLC272 because these allow the output voltage to go down to the negative rail. In this case, that would be ground. So my output does go from 0 to around 7 with this gain setting. If I used certain different op amps that can't go toward at least one of the rails, my voltage range with a 0 to 9 volt supply might only be minimum 2 volts and maximum 7 volts or so. Then, using the rest of the IOs, I have 2 push buttons. I don't really use them right now, but in the future I could do things like switch a channel between different waveforms or something like that. And there's 2 LEDs as visual rate indicators. Right now I'm just using one LED, and it's set to fade the brightness in and out at the rate of the frequency signal I'm generating. So it's a visual quick indicator of how the frequency is set. And on analog inputs, I have 2 potentiometers. So in the future, I could use those independently to set the rate of each output. But for now, I'm just using one potentiometer to control both at the same rate. All I'm really doing is trying to get a demo functioning. And in case I want to control some other things over I²C to make a more complex project, I have serial clock data and ground available on a header as well. So the brightness on the LED is being controlled with PWM, so it represents the frequency. I have a scope probe on the sine wave output and the triangle output, and the scope is in roll mode to have a better view of the low frequencies. So I'm going to apply 9 volts, and now the waveforms are starting. So once we get at least one cycle, it's saying the frequency is 0.19 hertz. And on both of those traces, the peak-to-peak voltage out of the op amp is around 7 volts as expected. So now, if I change the frequency, I'm going to zoom in so we can see that better. Now it's 9.9 hertz at the highest frequency I can get with the code in there. And the LED is blinking at that rate. I'll slow it down somewhat. Here it's 2.2 hertz, and here it's around almost 0.8 hertz. If I wanted the signal to be even slower than around 0.2 hertz. I could just add more delays in the software so that it generates an even slower signal. And if I wanted it faster than the current 10 hertz highest frequency I can get, I could either change my data table so that there's less samples and it can get through faster and generate waveforms, or keep the same data table but use a direct digital synthesis method of just skipping through the available samples to speed up the waveform, as long as it's still generating a reasonable representation of the expected waveform. As a demo of using an LFO in a couple of different ways, I have a 555 audio oscillator setup going to the orange amplifier. It's going through this audio jack, and on here I have a resistor and then a Vactrol, which is a light-dependent resistor and an LED enclosed in a package so that the only light hitting the light-dependent resistor is from the LED. And I'm using that as a volume control with a voltage divider between the fixed resistor and the Vactrol resistor. That looks something like this. So the low-frequency triangle waveform is going through the fixed resistor, and then in this Vactrol there's an LED connected to ground. So as this voltage goes from 0 slowly up to 7 volts and then back down, we get different amounts of forward current on this LED, so it gets brighter and dimmer. That shines on this light-dependent resistor and gives us more or less resistance as the data sheet for the specific part would indicate based on a certain forward current. So this resistor here is changing as the LFO changes. We have our oscillator generating a tone that's going into a fixed resistor and LDR voltage divider. And based on where this LFO is currently at and how bright the LED is, the resistance and the overall volume are going to be impacted. So I'll turn the speaker on. It's not the smoothest volume up and down. We're just doing it for an example. So it's going to ramp up and down in volume relatively slow and a bit jumpy. Then I'll change the rate. So it's just an example of using an LFO to control another circuit element. And in this case, we're using it as a voltage-controlled oscillator. If we take the LFO and put it on the control voltage pin of the 555, if we set this up so we're controlling both volume and pitch, we'll hear the volume come up and down, and we'll hear the frequency change as well. So I'll connect to the control voltage pin, turn on the amplifier again, and we should hear pitch and volume change. I was changing the overall 555 oscillator pitch as well. So when we have the audio level as well as the frequency of the tone changing in a certain way, it almost sounds like there's an echo effect. So that's where having LFO control of other circuits can come in useful.